Well, in this lecture, you would find some solved problems related to settlement, or you can say the settlement analysis. Well, first look at this solved example, consolidation differential settlement in non-uniform soil. The statement of the problem is the foundations supporting two columns of a building are shown in figure. An extensive soil investigation was not carried out, and it was assumed in the design of the foundation that the clay layer had a uniform thickness of 1.2 meter. 2 years after construction, the building settled with a differential settlement of 10 millimeter. Walls of the building began to crack. The doors have not jammed, but by measuring the out of vertical distance of the doors, it is estimated that they would become jammed if the differential settlement exceeded 24 millimeter. A subsequent soil investigation showed that the thickness of the clay layer was not uniform but varies, as shown in the figure that I showed on the previous slide. The owners would like to get an estimate of the expected total differential settlement and how long it will take before the doors become jammed. Now, in this question, we would follow that strategy. Determine the settlement under each foundation and then calculate the differential settlement. Since you know the differential settlement that occurs over a 2-year period after construction, you can find the degree of consolidation and then use this information to calculate the expected time for the doors to become jammed. The solution, the step 1. Calculate the vertical stress increase at the center of the clay layer under each foundation. Let's use the approximate method. So by using that method, by using this formula, we can calculate sigma ZA and the sigma ZB, which are 30 kPa and the 42.2 kPa respectively. Then the step 2, calculate the primary consolidation settlement, and we can use this formula H naught into M sub V into delta sigma, and just by plugging the values we can calculate the primary consolidation for A and the primary consolidation for B, which are 25.2 millimeter and 82.7 millimeter. Well, step 3, calculate the differential settlement. So obviously the difference of these two values will give you the differential settlement. Next step is to calculate the time for 24 millimeter differential settlement to occur. Current differential settlement, that is 10 millimeter. So degree of consolidation is equal to 10 divided by 57.5, so it is 0.17, and then the time factor, it can be calculated by using this formula, that is 0.037, and then the coefficient of consolidation, and considering the double drainage, you can get it 0.036 meters square per year. Now for 24 millimeter differential settlement, obviously the degree of consolidation would be 24 over 57.5, that is 0.42, and then you can calculate the time factor by using this approach, and that is coming 0.225, and then the time you can calculate by using this formula, and that is coming 12.25 years. So you can say that therefore in the next 10.25 years, because you can see that 2 years have already been spent. So 12.25 minus 2, so that means therefore in the next 10.25 years the total differential settlement would be 24 millimeter. Okay, the next problem, settlement of a levy. Statement of the problem: a recently constructed levee along embankment is shown in the figure below. It was constructed from compacted earthen fill, that's rolled fill. Statistical analysis from climatic data and other data such as historical wave heights show that a freeboard of 1 meter is required. If soil settlement is not considered, determine how much the freeboard would be compromised, and estimate the settlement profile under the levy. Only a limited set of data was available for the soft, normally consolidated clay. These data are moisture content 55.6%, liquid limit 68%, and the plastic limit 30%. Now look at this figure. We are having this soft, normally consolidated clay, and then we are having the sand and gravel, and then the impervious stiff clay is present. And look at the levee, the shape. So in fact it would not be wrong to say that there are two triangles loading up to this and this one, and here you are having the rectangular one. Well, there is slight you can say misprint. This 4 meter is basically up to this point, from this point to this. In fact, we are considering this particular point, which is just the starting of this triangle, and this is just the end of the triangle, that is point, you can say this one, and this is you can say just the start of this triangle. The end of the triangle is over here, and just at the center of this rectangle we are having this. So we are going to consider the 3 points, point 1, point 2, and the point 3, which are present at the center of the soft, normally consolidated clay layer. But you can see that the thickness of this layer is not uniform. So just take this thing that this 4 meter is from this point to this point. So I will repeat, if you just consider this one, so starting from here and ending from here, this is 4 meter. Now look at the figure again, and look at the strategy that we are going to adopt over here. The soil data are extremely limited. You can use empirical equations to estimate the compression index. To find the vertical stress distribution, use a combination of surface strip load with uniform stress distribution and with triangular stress distribution. So here you can see that we are having the uniform stress distribution in the middle, this one, because of that, and we are having the two triangular stress distribution. This one, this is one triangle, and this is another triangle. Now in this problem we are going to consider the triangular stress distribution and the uniform stress distribution. So you will have to look at this figure. Uniform stress distribution is present over here, and if you are interested in this element, so delta sigma x can be calculated by using this formula, and the vertical stress over this small element, it can be determined by using this formula. Now here you can see the triangular distribution, and in this case if you are interested in this element or point, and delta sigma x can be calculated by using this formula, and this one will be used for vertical stress at this particular element or point. So we will be using these concepts in this particular problem. Now the step 1 for this problem: estimate soil parameters and calculate surface stress. So you can use this empirical relationship, and with the help of liquid limit you can calculate the compression index, and that is coming equal to 0.52, and Q sub s, that is obviously gamma into the height, the maximum height of the levee, that you are having 6 meter. So taking gamma as 18 kilonewton per cubic meter, so it is coming 1 of 8 kPa. If you just look at the compressible soft clay layer, that is basically in the submerged condition, so the degree of saturation is obviously 100%. So we can use this formula: E naught is equal to WGS, and this is 0.556 multiplied by 2.7, so it is coming 1.5. And then this is the formula for the submerged unit weight: GS minus 1 over 1 plus E naught, and that is coming 6.7 kilonewton per cubic meter. Well, keep this in the mind that the submerged unit weight or the buoyant unit weight, it is equal to saturated unit weight minus unit weight of water. Okay, the next step is estimate increase in stress at the center of the soft clay. So 3 points are being considered at the center of the soft clay as shown in the figure. As I showed the figure on the figure present on the previous slides, the increases in vertical stresses calculated from those 3 points are shown in figure below. So we are going to consider this as point 2, this as point 1, and this as the point 3. So 3 points are present at the center of the compressible layers. So you can see that point 1 is just at the center of the uniformly distributed loading, and point 2 is lying at the end of this triangular distribution, and point 3 is lying at the end of this triangle. So here look at that. We are having the Q sub s, that is obviously 108 kPa. We calculate from here. Then B, that is the horizontal distance that we are considering. For the triangle, obviously this x would be measured from this starting point. So obviously this is 12 meter. And for this one, the central part, obviously this is 4 meters, so that's why 444 is written. But again, in the triangular case, axis will be measured from this point, so this is 12 meter, so that's why it is written. X is the distance which I showed on the previous figure, so that is 12 over here considering that triangle. But when you are considering this one, that is the central part, it is 0 over here, 2 over here, and 4 over here. Again, for the triangle, as x is being measured from this point, so this is 12. And z is the depth up to the center of the compressible layer, clay layer. So that's 1.6, 1.6, 2, 2.2, and 2.2. And then delta sigma z, that is the increase in stress at the center of the soft clay, the values are written. Just to explain that thing, that how we have got this value of 49.2, you can look at this one. Some calculations are given. Tangent inverse z over x, that is equal to 7.6 degrees. So alpha angle that I showed on the figure that I showed earlier, that is 90 minus 7.6 minus beta, and the beta is 0 over here. So when you will convert that angle into the radians, so it is 1.438 radians. So delta sigma z, that is qs over pi into x over b into alpha, and that is coming 49.4 kPa. So that's why you can see it is written over here. Similarly, if you just look at this one, you are getting it because of that tangent inverse z over x, that is tangent inverse 2.2 over 12, that is 10.4 degrees. Then you know the alpha, that is equal to 90 minus 10.4 minus beta, again beta is 0, so that's 1.3 radians, and then delta sigma z is coming equal to 47.8. But here if you just look at the center, 88.2, 88.4 is just because of this rectangular loading. But obviously you are having the effect of this triangle and this triangle, so that is 17.2, that is 8.6 from this triangle and 8.6 from this triangle, and in this way it is coming 17.2. So over here it is totally is 88.4 plus 17.2. While some description is mentioned that I have already explained, the additional vertical stress increase of 17.2 kPa at the center of the levee is due to the two triangular loads. The input to the stress program for this stress increase is QS is 108 kPa, B is 12 meter, X is 12 meter, that is 12 meter plus 4 over 2 meter, and Z is 2 meter. You have to double the result because you have two triangles. So either software can be used, or you can use the method to determine the stress, and you can get it by that. Step 3, estimate the settlement. Since the soil is normally consolidated, so OCR over consolidation ratio is 1. So use this equation, which is applicable to the normally consolidated soils. So you are familiar with that. So looking at the point 1, 2, and 3, the height of the compressible layers are mentioned. Then the delta sigma z that we have just calculated on the previous slide, you can write these values over here, and that is basically the overburden pressure, because in the center of the clay layer. So that value, if you just add these two, you are getting 119. 102.1 plus 10.7, you are getting this one, and similarly by adding this and this, you are getting this, and then just by plugging the values in this formula, you can calculate the primary consolidation. The settlement at the edges of the levee base would be approximately 0. Yes, even you can employ your common sense. Note that although the vertical stress increases at point 2 and 3 are about the same, the settlement at point 3 is greater because the thickness of the soft clay is greater there. So this point is very important, and I would like to narrate this one again. The settlement at the edges of the levee base would be approximately 0. Note that although the vertical stress increases at point 2 and 3 are about the same, the settlement at point 3 is greater because the thickness of the soft clay is greater there. So the average reduction in freeboard is the average of the three values, 4.79 plus 0.68 plus 0.81 divided by 3, so it is 0.76 meter. Now here you can see the sketch of the settlement profile. So you are having this one, look at it. You are having maximum settlement of 0.81 millimeter, 0.81 meter over here, 0.79 meter over here, and 0.68 meter over here. Okay, now you would find some more solved problems. So you can go through all these problems yourself. So for example, if you just look at that, an odometer consolidation test is performed on a normally consolidated clay stratum that is 8.5 feet thick, and it found that clay's initial void ratio was 0.8 and its primary compression index is C sub C is 0.28. The in situ stress at mid-clay layer is 2650 psf and the building exerts a pressure through its mat foundation of 970 psf. The secondary compression index is C alpha, it is 0.02. The time of completion of the primary settlement is approximately 18 months. What's the total consolidation of the 8.5 foot clay stratum 5 years after the primary consolidation? So it's an interesting problem. You would find the solution, step-by-step solution of this problem on the following slide. So you can go through this problem yourself and then look at this problem. Estimate the average settlement from primary consolidation of clay stratum under the center of the bridge pier. So bridge pier is being considered, profile is given, and you would find the solution on the next slide. So look at that. So you will have to use those all different concepts that we have studied in the previous lecture related to settlement analysis. Well, if you just look at this problem, an odometer test on a 1-inch thick doubly drained sample from the clay stratum shown below attained 50% consolidation in 6.5 minutes. Find the total differential settlement of the fully loaded tank, the time required for 75% consolidation in the field, the depth of excavation for minimal settlement. So you can see the profile. Water table is present over here, and this is the solution. And this problem, a uniform surcharge of sand 20 feet in height will be placed over the marl stratum as shown below in order to pre-consolidate that layer for a future building. The in situ void ratio of the marl is 0.59 and its index of compression can be found from a relation proposed by Sauer as C sub C is equal to this. So this is the relationship, good relationship given by the Sauer. Find the total settlement of the surcharge at its point A. So this is the point which is being considered over here, and the coefficient of consolidation C sub V can be calculated by using this formula. So these are the new formula that we are going to use in this particular problem. So you would find the application of these formulas in this particular problem. So this is the time along horizontal axis and the percent consolidation along vertical axis, and the solution you would find in the following slides. Next problem, an odometer consolidation test was performed on a clay sample 3 cm high, drained on both sides and taken from mid-stratum shown below. 70% consolidation was attained in 6.67 minutes. Find the time required to attain 70% consolidation of the clay stratum, the magnitude of the settlement in that time. So this is also an interesting problem, and the solution is on the next slide. And after that you would find this problem. An odometer test was performed on a peat, that's highly organic soil, from an FDOT project in the Homestead area. The results are shown below this in the table. The initial sample thickness was 20 mm with two-way drainage through porous stones, simulating field conditions. The vertical stress increment is 10 kPa. Use an estimate of the coefficient of consolidation C sub V by using this formula in this particular case. So you will have to plot a graph of settlement against the square root of time you will have to determine the value of C sub V, then the estimate, what could be the good estimate of the elastic modulus of this soil, what sort of permeability K can you estimate for this soil from uh, elastic modulus. This is the solution, and then you would find another problem. The statement is given over here. We are having the same charge in this case, and in this way, different problems you would find, and this is the problem that is showing the bearing capacity of a 30 feet thick medium dense sand stratum with phi is equal to 36 degrees and gamma is 112 pcf is 3 ksf. Column A has design load of 430 kps and column B has a design load of 190 kps. Select footing sizes and determine the differential settlement delta delta z between them. Is this delta delta h acceptable for columns spaced 30 feet apart? So it is also an interesting problem, so you can go through it yourself. So in this way you find a number of problems in this particular lecture. So to have the clear feel about these problems, first you will have to go through the previous lecture in which you are having the details about the different methods or different concepts used in the settlement analysis. So when you are having a grip on those approaches, then you would be able to solve these problems very easily. So that's all for today. Thank you.